Thank you very much. I'm Hyunbae Park from Yes. First, I'd like to say it's really great honor for Park family to be invited to RESCEU Symposium and also be a part of celebration of Suto-san's starting new life. I'm also enjoying the meeting because I able to meet many friends of mine, including Renyu, Kang, and Ofro, and so on. Today, I'd like to report a new measurement of dark energy crystal state W using Alpha-Paczynski test. So it was motivated in the year of 1990. So November 1990, I was visiting Princeton, and Bodan wanted to have lunch with me, and he came with a paper, this Alpha-Paczynski paper. And he told me that he thinks the idea is wonderful, but nobody was working on it. So he asked me to work on it, and I made a promise, but I only started in 2008, 18 years later. And by that time, he passed away, and this paper, I'm talking about this paper today, and this paper is dedicated to Boda. It works in this way. Suppose we have an object for which you know the size. The line of sight direction are parallel, and the size across the line of sight are perpendicular, and they are related with observational quantity delta z and delta theta according to this relation. And if you are not interested in absolute size, but only in the shape, and then you can take a ratio, and this ratio will depend on this combination of angular diameter distance and Hubble parameter. But when you make a mistake in choosing cosmology that is used to convert redshift to moving distance, the shape will be distorted by this factor. So we call this product of dA and H as a distortion factor. Some time ago, when I was writing this paper, I went through all the literature. Fortunately, there are not infinite number of papers on Alpha-Paczynski test, so I was able to review basically all the papers, and I listed some of the influential first papers introducing a particular method and particular targets. And I found Matsubara and Suto's paper, written in 1996, introducing two-point correlation function as a standard shape, and this is the paper. And I realized later that I'm basically extending his introduction made in 1996. So here's a concept diagram of the application of this Alpha-Paczynski test. Suppose you have a redshift catalog of galaxies giving you angular position and the redshift, and you adapt the cosmology to convert redshift to moving distance R, and make a map like this, and then you divide the sample into two different redshift shells and calculate the angular correlation function in each bin. And then you compare the shape of this redshift space correlation function, and if there is any difference, apart from the difference you already expect, then that indicates that the cosmology you adopted at this step is not correct. So you iterate until you reach a certain cosmology which makes the redshift space correlation function unchanging. So please note that here we use only the shape of correlation function, and it doesn't depend on the amplitude. So in principle, it is a geometrical method, and should be independent of all kind of evolution. Okay, so we adopt the shape of redshift space correlation function, meaning that we use redshift space correlation function normalized by this integral out to sufficiently large this separation. And also we use the differences across different redshift shells. For example, if you have data built into these 4 different redshift, and then you take the difference between these redshift spaces correlation function. And the differences are here. And if you compare these color bars, the amplitude of redshift space distortion itself is 10 times bigger than the redshift evolution. So you can, this is roughly the standard shape. So as I write here, the redshift space distortion effect itself is big, but the redshift evolution of this redshift space correlation function is smaller. So that's the main idea. We use surround data. Right now we are analyzing DESI data, which is sitting over here with much higher number density. But today the result is basically coming from the existing surround survey data, which is broken into 7 redshift shells. We basically ignore this EBOS data. So effectively we have 6 shells. PR7 and SSS3, LOSI, and CMAX. These are the redshift space correlation function in those 7 shells. The colors are the correlation functions. If we stack them in one panel, this is the result. So you can see they are roughly, their shape is roughly the same, okay? Even though the redshift changes from effectively from 0.08 to about 0.7. Here I've adopted omega matter and W to be 0.26 and -1. Okay. So we adopted lambda CDM model to calculate this angular, the redshift space 2-point correlation function. Many numerous gray lines are the correlation function of mock samples, simulating each of these subsamples. And you can see they roughly agree too. But there will be a better model if you actually compare the shape in details. You arrive at different cosmological model. So we use cosmological models to measure the systematics. There are a few systematics, mainly from gravitational evolution and also the galaxy bias and so on. So we basically measure this systematic bias and the difference of this redshift space correlation function in different redshift bins using large n-body simulations and in many sets of a little smaller simulations with different cosmological parameters. And all the other cosmological models are interpolated out of these 10 multiple simulations. I'll skip this part. I'll only mention this one. So we fix all the cosmological parameters except for 2 parameters that governs the expansion history of the universe, and they are omega matter and W. So it's basically a family of wCDM, flat wCDM model, and we have freedom of choosing omega matter and W. Okay, here's the result. So we measure W to be minus 0.9 with the uncertainty of about 2% and omega matter of 0.29. And that is the combined result among our alpha-pacinic test, which is pink, and supernova, which is green, and BAO, which is yellow. So our alpha-pacinic test constraint is much smaller, tighter than compared to supernova, and parallel to that. So supernova is basically doesn't help, whereas BAO has some angle to our degeneracy element. So that is helping us to reduce the error a little bit, and that's how we get it. So this is the result combining these three load data. We didn't combine CMB. So in 2016, we used exactly the same data and got result that W is consistent with -1 because we combined our data with CMB. So once you combine your data with CMB, you again get W consistent with -1. But if you, but now we are able to get interesting constraint on W even without CMB. So that's why I didn't include CMB. And what is important is this. So now, this W, our measurement has such a small uncertainty that now we can say W is almost inconsistent with -1 and greater than -1. So that's 4.2 sigma away from -1. And once we combine our data and other logi data with CMB, then it becomes consistent with -1. Okay? So that's another kind of double tension. Okay, so we all know the major component of the energy of the universe, and we are wondering what the nature of this dark energy. And today, I'd like to say that at least the lambda CDM model as is inconsistent with the late time expansion history of the universe. And if our measurement of W, effective W, averaged over ratio about 0.6 or 0.7 to 0.1, greater than -1, that may imply that dark energy is actually not cosmological constant, but some dynamic quantity like k-essence or quintessence. Okay, so that's the end of my secondary part of my talk. This is my main part of my talk. Okay? So I'd like to recall some occasions I encountered with Suto-san. So it was February 1990 when I met him for the first time. And at that time, I was working on cosmological embodied simulation using 4 million particles to prove that the gravitational evolution instability model can produce structures like CFA great wall. Okay? And so we are focusing on the appearance of this large structure. But then J. Osterreicher looked at it and he thought that is okay, but he said the filaments are hotter in our simulation. So one day he asked me to come to his office, and where I found Suto-san was there. Okay? And he recommended me to measure the Mach number. So in my paper, in the same paper, I actually cited his calculation for spiral galaxies and for elliptical galaxies. They measure Mach number to be 2.2 and 1.3. And if I use at that time, the standard model of CDM model, I get much smaller Mach number. So as an alternative, I chose omega H.2 model out of no reason. I just chose that. And then I found Mach number is much bigger and begin to be consistent. So But then, actually, 2 years later, I analyzed the CFA data and measured power spectrum, galaxy power spectrum for the first time, and the model consistent with that power spectrum was actually omega h equal 0.1. So that was a great influence, actually, by Suto-san. Okay. So that was 1990. So after then, we have occasionally encountered some places. Also, I read many of his embodied simulation papers. But after 2004, we begin to meet more frequently, and that was mostly because of this our PIAS cosmology workshop, and also our participation of Sloan. So this is the very first the PIAS workshop held in 2004, and thankfully he participated the very first one. We also visited ancient, not very ancient, but probably 600 years old astronomical observatory sitting in one of the palaces, and also we are much younger, 19 years young. Okay. And also we visited Apache Point Observatory in 2005 and took this beautiful photo together. Okay, then as I told you in this talk, my work after 2008 was actually continuation or extension of his work done in 1996. He also maintains very good relationship with my son, Hyunbae, sitting over there. Okay. Thank you very much. Okay, so this is the animation I made last night. So I'd like to thank so much to Suto-san for guiding us in many fields, and also thank for his great contribution to observational cosmology. And I wish him to lead us, continue to lead us in the future. Thank you very much.
So, questions, comments? Yeah. Okay. No. Maybe yeah. Over. Yeah.
Hi. Thanks about your interesting outlook. But just curious, do you think there's a scope if you do it with redshift to constrain the time variation of WA?
Yes. Right now we are analyzing this data, which allows us to reduce error bar. So that also allows us to adopt one more parameters. So the next model we are going to constrain is this time varying W cosmological model. Yes.
Thank you.
Okay. Yeah.
Next year.
Thank you. If this is true, really big discovery actually. So I'd like to just make sure that which BAO data you use is a DR16 and both from same galaxy cluster galaxy data set. So AP you are using.
I think this, whatever it is, this is the latest, and this is BAO only. BAO only. Yes.
So then however both from same data set. So probably AP test you are using maybe slightly smaller scale compared to BAO scale. BAO scale like 100 megaparsec. AP, which scale are you using?
We are using correlation function from 6 to 20 megaparsec.
Oh, okay. And sorry, did you include covariance or something? No, maybe not.
Yes. So the likelihood analysis.
No, I mean BAO and AP. Cross
Oh,
covariance.
between BAO, no.
Hi. Yeah, thanks for the talk. It's really interesting. I had a few comments. So, first one, I don't think you can combine that with the CMB, right? Because you shouldn't combine things that are discrepant, because then you get nonsense. So,
Which one?
So the BAO plus AP plus SMs, I don't think you should combine with the CMB because that looks very discrepant.
we use only these two.
But just because earlier you said if you combine with the CMB, you go to -1, but I don't think you should, from a statistics point of view, I don't think you should do that.
Why not?
Well, you should not combine things that are discrepant between them because.
Okay. In that sense, yes.
But I was wondering because you in the likelihood part, maybe I missed it, but do you have just like omega, like those two parameters? Like, is there no, do you know, marginalize over other cosmological parameters or any
Other cosmological
systematics?
parameters are fixed to the CMB models.
So I wonder if that would increase your error bars a little bit if you allow them to vary.
Right. So I should actually say that we are actually measuring W, okay, in absolute sense. We are only falsifying a model which has a set of cosmological models. Okay? And I'm saying that W cannot be -1 in that case.
Yeah, I see that. Thanks.
Okay, no questions? Okay, then let's thank the speaker.
Thank you very much.